Hello everyone. Today I want to talk to you about one of my absolute favorite topics in math, and I want to talk about solving it in one of my favorite ways. We're going to talk about derangements, and we're going to solve it using the multiplication principle, which some people call the rule of product. I want to show this because it's this really elegant and clever way to go about solving problems of derangements, but it's tricky. Once you see it, you get it, but it kind of takes some time. So in case there's anyone out there who saw it in class and said, I think if I just saw it again, I could really get it, I want to show that for you. So here's the setup for the problems. It starts as so many combinatorics problems do, with 5 people in a line. Now a totally reasonable question one could ask is, how many ways can we arrange these 5 people in these 5 chairs? Well, that's just how many ways can you put these 5 people in a line. Each of these arrangements is called a permutation. It's just a question. That question would just be, how many ways can you permute 5 objects? And we of course know that to solve that we just do 5 factorial. If you're using the permutations formula, there's a little hidden 5 minus 5 factorial below there, but that's just 0 factorial, which is 1. So it doesn't make a difference. Now, a slightly more pessimistic question would be, how many ways can we arrange these 5 people in the chairs where no one is in the chair that they started off in? The blue guy doesn't end up in the blue chair, the yellow doesn't end up in yellow, and so on. And that's a question of how many derangements there are. And for derangements we use the shorthand D with a subscript. So D5 would be how many derangements are there of 5 objects. So the question is, how do we calculate this? I think a good starting step is maybe to try smaller cases. Trying smaller cases is a good problem solving strategy in general when you hit a math problem you don't know. You're trying to come up with a formula for n. If you look at the smaller cases, maybe you can find a pattern. And those smaller cases are often easy to figure out, even if you don't know a general solution. So, let's look at the smaller cases. To help us keep track, I'm going to make us a little table, if you don't mind. So first we'll look at n equals 1. How many ways are there to derange one object? This blue guy starts off in the blue chair. Is there any way to rearrange it so that he doesn't end up in the blue chair? No, it's the only option. There's no derangement of one object because no matter what, the only permutation, he's in the same spot. So D1 is 0. Let's try 2. Of all the ways that we can arrange this, how many don't have anyone in the same position where they started? I think it's pretty straightforward. We've got this guy here, this guy here. Is there any other way? No. So D2 is 1. There's one way, there's one derangement of 2 objects. Next we'll try 3. How many ways can this happen? If we're trying to derange 3 objects, we'll see first where we could put the blue guy. The blue guy could go here, and then, since he can't go here, he'll have to go here, she'll have to go there. That's one way to do it. Then jot it down just so that we don't lose track of what we've done. And it looks like that's the only derangement that involves the blue guy here, because otherwise the red would be here. And so we'll also see, what if the blue guy goes here? Well, yellow can't go there, so yellow will go there, red will go there. And that should be our only other derangement possible. So it looks like we only have these 2 derangements of 3 objects. Naturally, the next step is to bring in a 4th guy. Phew, I think that's all of them. Let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks to me like you can make 9 derangements of 4 objects. Now that took me a while. I don't think it's worth it to figure out 5. If push came to shove, could I list it out? Sure. Is it worth it? No. I think 5 is when we need to start saying, is there a pattern, or do we need to find a better way to do this? Do we see a pattern? At this point it doubled, and this point it more than quadrupled. I don't see a pattern, which is sad. So we need to find a more systematic way of counting derangements. The first way we're going to do that is using the multiplication principle. The multiplication principle is that rule that says that if you have 2 shirts and you have 3 pair of pants, the number of outfits you can make is 2 times 3 is 6. So we're going to use this, but instead of doing number of shirts times number of pants, we're going to say the number of ways you could derange 5 objects is the number of ways you can choose to place the first object times the number of ways you could choose to place the rest after that. So the number of ways you could place the first object, well, he can't go to his own chair, and there's 4 others that he can go to. Okay, there's 4 ways to place the first object. Now the number of ways to place everyone else is the harder part. After we have placed the first person, what are we left with? Let's say the first person took this chair. I'm having him take that chair, but it actually doesn't make a difference, because no matter which chair it takes, you're always going to be left with 4 people and 4 chairs. 3 people have a corresponding chair, and then there's 1 lone person and 1 lone chair. After the first person takes the chair, the number of ways to place everyone, well, either this person's going to take either the lone person's going to take the lone chair, or the lone person is not going to take the lone chair. So the number of ways to place everyone is just the number of ways to place them where he does take the chair, plus the number of ways to place them where he doesn't take the chair. So what does this come out to? So we want to know the number of ways that the lone person does take the lone chair. If the lone person does take the lone chair, now how many ways can this happen? Well, it has to be a derangement, so none of them could take their own chair. So we not want to know how many ways 3 people could be seated in 3 chairs where no one gets their own chair. That's by definition D3. It's the number of ways to derange 3 objects, which we did calculate before, and we said was 2. Now, if we want to know the number of ways if the lone person does not take the lone chair, okay, so this person cannot take this chair, this person can't take this chair, this person can't take this chair, this person can't take this chair. How many ways can that be arranged? Well, they can't take their own chair, and this I'm going to just call his own chair. But they can take any other chair. That's by definition. D4, which we said was 9. So we now know that D5 is just going to be 4 times 11. Now, wasn't that just so much faster than trying to list out all the possibilities? So how do we generalize this? Well, we can figure out, in general, the number of ways to derange n objects using the exact same strategy. We could say the number of ways to derange these n people is the number of ways to place the first person times the number of ways to place everyone else after that. If we have our people, with our n people and n places to go, the number of ways to place the first person is what's out of the n of them, it's everything but the first. It's n minus 1 of them. And how many ways are there to place everyone else? Well, after the first person has already gone, it's just like last time. The lone guy could either take the lone chair or not take the lone chair. If the lone person takes the lone chair, then there are dn minus 2 arrangements. And if the lone person doesn't take the lone chair, it's just like everyone else then, with a chair below it that can't go with it. So it's dn minus 1. And this gives us a formula for counting derangements. What's good about it? It's beautiful. What's bad about it? It's recursive. It's going to be a lot of work to try to use this on paper by ourselves. If we did, D of 100, well, we would have to know D99 and D98. And to know those, we'd have to know D98 and D97. And it just keeps going down. So is this the formula we're actually going to use in real life problems for big values of n? No. But it's great exercise in using the multiplication principle in a really elegant way. And it just gets us excited about finding an explicit formula for counting derangements, which we could do in another video using the inclusion-exclusion principle. If you have any questions, leave them in the comments section. I'm sure someone on YouTube will answer. The internet is full of nice people. Thanks for watching.